All right, physics. You have a theory test tomorrow at 11 o'clock. Again, we'll do that via Zoom meeting so that I can say I saw you. And it honestly won't take long. You should have the notes for the first two sections because, believe it or not, we did those before we left the building. And then the last two are up on Google Classroom. I think one's March 24th and one's March 27th or something is where they are. But they're in their appropriate sections. So we're going to start into this section. Any homework I give for it, though, won't be due until Monday. Won't be due until Monday, so you'll have the weekend to do this. So chapter 11 is called Projectiles and Circular Motion. So we're going to deal with projectiles and circular motion. It is a very short chapter. Just a warning right up front. There's only 2 sections. They're not long. So just be prepared. If I say, hey, we're coming to the end of the chapter and it feels like we just started it, that's because we did. Projectile motion is section 11.1. So I want to talk a little bit about the theory. I'm going to, like I said, I'm going to put up the PowerPoint, but I want to discuss it a little bit. So when we talk about projectile motion, a projectile is anything that moves in the air, and the only force acting on it is gravity. And so it's given what's called an initial thrust. So a bullet is a projectile. So the initial thrust is the firing of the gun. If you shoot a basketball into the net, you give it an initial thrust, and then the only force acting on it as it goes through the air is really gravity, okay? The trajectory is just the path that projectile makes. So if you were to stand on the balcony where we dropped our eggs from in the church, okay, and if instead of just dropping it straight down, if you had thrown it forward, it would take more like this path. Actually, it would take more like this path. And the path that it takes is just called its trajectory, okay? The horizontal distance that it travels is called the range. So the horizontal distance, so rather than dropping right below you, it actually dropped way out here. That horizontal distance that it traveled is called the range. Now, air friction does affect the trajectory. We know that. But the math needed to account for air friction is really complicated, and so we don't do it. So we're actually going to just totally forget the fact that there's air friction. We're going to assume we're dealing with ideal situations every time. And we actually don't need any new concepts, any new formulas to do this, all right? No new formulas in here, but I mentioned it in another video. You are actually going to be, will you stop? You are actually going to be using uniform motion problems. So those ones like distance is equal to, or displacement is equal to initial velocity times time plus 1/2 at squared. You're going to be using that. And ones like it. So you may want to pull out that formula sheet again. So all you need is the data that will provide you with the velocity of the projectile at the moment it's launched and all those equations that we already know. Hey. The horizontal, no, stop. The horizontal motion of the projectile doesn't affect the vertical motion. So the fact that will you stop? The fact that you throw it straight out has absolutely no impact on how it drops to the ground, okay? The vertical components and the horizontal components are separate, okay? They are separate. So the fact that gravity is acting on it has absolutely nothing to do with how fast it's going horizontally. So you have to treat horizontal and vertical separately. Now, they have some tips on page 533, and I have listed, it's a list, I have listed them for you on the PowerPoint, but they're very helpful to keep in mind when you're doing these questions. And if I can just get you to hear me, it will actually help. So the first thing is that gravity is the only force influencing projectile motion. Gravity is the only force involved. So when we're talking about forces, we will only be dealing with the force of gravity. All right? Number 2, gravity only affects the up and down motion, the vertical motion. It doesn't affect the horizontal motion at all. All right? So gravity affects only the vertical motion. So the equations for uniform accelerated motion apply. In other words, there's no acceleration horizontally. There will be no acceleration horizontally. Horizontally, it's all uniform motion. The velocity stays the same. If you throw it this way at 5 meters per second, it continues going this way. Will you stop? At 5 meters per second. It just continues this way at 5 meters per second until it hits the ground. It's accelerating downward, but horizontally it's not changing its speed at all. All right? Again, we're neglecting the fact that air would be slowing it down horizontally. We're ignoring that. Number 3, no forces affect horizontal motion. There is no force that is affecting horizontal motion. So we use the equations for uniform motion. Number 3, and this is a big one. Sorry, number 4. Number 4, this is the big one. This is the most important one. Listen to this part. The horizontal and vertical motions are taking place over the same time interval, okay? If it's going across for 3 seconds, it's also falling for 3 seconds. So the key is that time, time is the link. It is the common thing between the horizontal motion and the vertical motion. Time is your link. So very often figuring out time is going to be one of the things you want to find right away, okay? Time is going to be one of those things that you want to find right away because you can use it in both the vertical and horizontal components because it's the same for each thing. All right. So basically they talk about the fact that if you had this scenario, so if you were dropping, let's say, a basketball from that balcony again, if you were dropping a basketball straight down or you threw it straight out, those 2 balls would actually land at the same time. We actually do this if we're at school, but we can't. But they actually land at the same time because the fact that you gave it horizontal motion has nothing to do with it falling, okay? So they talk about that a little bit, and that is their point with that. All right, we're gonna do one example, just one example, and that's it, I think. Yep, we're just gonna do one example, and we will talk about how to go about doing this. And again, no new formulas here, nothing magical, but please keep in mind time is the link between horizontal motion and vertical motion. All right, so it says we're hiking in the wilderness, because it's the only place you can go now to go for a walk. We're hiking in the wilderness, and you come to a cliff overlooking a river. So here's the cliff, here's the river. All right. Now, a topographical map shows that the cliff is 291 meters high. So the distance vertically, I'm going to assign to be y because that makes sense in my head. So the distance vertically is 291 meters. That's the information that I'm getting from that. Now, the river is 68.5 meters wide. That's a horizontal distance, right? But I don't know that it's gonna go, I'm just gonna put river is 68.5. You'll see why in a minute. So you throw a rock directly forward. So you're standing up here and you have a rock and you throw it directly forward. Can you see that little guy? All right. You throw the rock directly forward from the top of the cliff, giving it a horizontal velocity of 12.8 meters per second. So you give it a horizontal velocity, so that's horizontal x, horizontal velocity of 12.8 meters per second. Now, that velocity is going to stay constant. It's going to stay going 12.8 meters per second that way as it falls, okay? The velocity will change vertically. It won't change going across. The velocity stays, the horizontal velocity stays constant. That's important. The question is, did the rock make it across the river or did it land in the water? So when you threw it, how good of a throw was that? Did it put it into the water or did it put it on the other side of the river? Where did it go? Okay. And with what velocity did the rock hit the ground? So we're looking for a final velocity. Now here's what I want you to think about with that final velocity question. That is not a vertical or a horizontal velocity because when it lands, it's going to land at an angle. So we need to look at what is the velocity vertically and what is the velocity horizontally. Now we actually already know the horizontal bit because we know it's 12.8 because I said horizontally your velocity doesn't change. Keep that in mind. I've said that a bunch of times because it's that important. All right. So our first question then really is how far did it go across this way? Because we know the river's 68.5 meters wide, but they're saying did it land in the water or did it land out here? I don't know. So we're actually looking for our horizontal distance. That's what we're looking for. Okay. Now, I said that one of the things, so we're looking for dx. Your velocity is constant. Your velocity is constant. Hi. Your velocity is constant. So in the x direction, okay, so horizontally, in the x direction, your velocity is equal to your displacement over your time. And remember, I'm looking for my displacement in the x direction. I'm looking for dx, right? So my horizontal velocity is equal to my horizontal displacement over time. So can I go right there and figure it out? Because I do know my horizontal velocity. It's 12.8. And I want to know the horizontal displacement. But in order to figure that out, I would need a time. Remember how I said time is very often important? It is. And I have no way of figuring out the time horizontally because this is really about the only formula I have horizontally. So I can't figure out the time horizontally. But remember, that I said that the link between horizontal and vertical is time, because it's in the air the same amount of time, right? Whether you look at how far it goes horizontally or how far it falls vertically, it's falling for the same amount of time. So time is the link. So what we're going to do is we're going to say, if I can't figure out time horizontally, could I potentially figure out time vertically? So we're going to look at the y direction. But in the y direction, there is an acceleration. It is changing velocity because it's falling because of gravity. Gravity is pulling on it. So acceleration due to gravity is 9.81. So I happen to have this formula that says displacement is equal to initial velocity times time plus 1/2 at squared. So if I'm looking at this in terms of the y direction, my displacement in the y direction, I actually know that it's 291. It's got to go from the top of the cliff to the bottom of the cliff, which is a displacement of 291 meters. Now my initial velocity in the y direction is 0 because I'm initially just holding the rock. So my initial velocity is actually 0 times time plus 1/2 acceleration. Well, my acceleration is 9.81 because my acceleration is because of gravity. It's acceleration due to gravity times t squared. So it turns out I can actually figure out t with this because that's gone. So half of 9.81 is 4.9. So I can do 291 divided by 4.9 and take the square root. Again, I'm assuming that you can probably do that math. And that actually works out to be 7.7024. Now remember I said time is the link. If my time is 7.7024 seconds in the y direction, that's how long that rock is going to be falling. It's going to be falling for almost 8 seconds. Then that is also the time in the x direction, 7.7024. So now I can actually solve this. My displacement in the x direction actually turns out to be 98.6 meters when I pay attention to significant figures. And I'm paying attention to significant figures because that's an answer. That's one of the things they wanted to know. So remember that the river was only 68.5 meters wide, and I'm actually going to throw it horizontally 98.6 meters. So that means it's not going to land in the water, it's going to land on the other side of the river. Now, the second part of that question asked, when it does land, and now we know it's landing on the ground, when it does land, with what velocity is it hitting the ground? Now, velocity is a vector. It's got to have a magnitude and a direction. It is a vector quantity, not a scalar quantity. So if you only tell me how fast it's going, but you don't tell me in what direction, that's no good. All right? So again, I explained earlier that it's going to be hitting at an angle. We're actually looking for the final velocity here. So what we need to do is we need to figure out what is the velocity in the x direction, and I said we already knew that because they told us that it's 12.8, and it doesn't change, but the velocity in the y direction does change because it accelerates as it goes down. So what I really need to do is figure out what is the final velocity in the y direction. What would that be? And in order to figure that out, we have a formula. Again, it's back there. You can look for it. But final velocity, and again, we're talking about the y direction, so that's why I'm putting it under the whole y direction section. You don't have to do it that way. I'm just trying to make it as clear as I can. Is equal to the initial velocity in the y direction plus acceleration times time. That should be in your list of formulas somewhere. If it isn't, add it now. So I'm looking for this. I'm looking for the final velocity in the y direction. The initial velocity, remember, was nothing, right? When I first start to let go, it's not moving. So that is 0 plus acceleration, which is due to gravity, is 9.81 times time, which is 7.7024. Don't round off that time. Use the whole answer. If you just round it off to 8, then it's going to throw your answer off. There's a few of you, and by a few I think I mean about 2, maybe 3 at the most, but I'm thinking mostly of 2 of you who have a tendency to round things off throughout your calculation, and then your answer is off, okay? So please don't do that. Use your whole thing. And so when I work that out, the final velocity in the y direction turns out to be 75.561 meters per second. All right? So that goes here. So what I actually have is a nice little right angle triangle, right? I've got the y, I've got the x, and I want to know the hypotenuse, which means I'm going to do Pythagorean theorem. So to do Pythagorean theorem, I'm going to use the velocity in the x direction, which is 12.8 squared, plus the vertical velocity, which is 75.56. Again, I'm not rounding that off. Squared is equal to final velocity squared. So don't forget to take the square root. So 12.8 squared plus 75.5 squared, take the square root of that. Works out to be 76.6 meters per second. Again, that is not the whole answer. That's the magnitude. That's how fast it's going. But what about the direction? The direction is tan theta is y over x. And so again, my y would be 75.56 and my x would be 12.8. And so theta ends up being, and I'm cheating because I don't want to get out my calculator, ends up being 80.4 degrees. And what you're actually finding, right, you're finding this angle because it's opposite over adjacent. So it's 80.4 degrees from the ground, with the ground. So it's almost hitting at a 90-degree angle. You threw that pretty straight out there because it's really hitting at an angle. This angle would be 80.4 degrees. So my answer is 76.6 meters per second at 80.4 degrees. And I don't care, degrees, units actually have nothing to do with significant figures. So if you wanted to, you could just round that down to 80. That would be fine by me. All right, that's it. Hopefully you've taken some of that in. Again, I can't say it enough. Time is the link. If you can figure out time for one piece, you can use it in the other piece. You're going to need those formulas back from, I think it was chapter 3, when we were talking about motion and vectors and everything. And I will post some homework. Again, that won't be due until Monday morning. I will look for it by 8 a.m. Monday morning. And that's it. Good luck on your theory tests tomorrow.